You are not safe. The Earth is not safe. At any moment, there is a chance of complete devastation, a maelstrom of fire and terror, a looming threat so great it could purge the entire planet of life. Like the sword of Damocles, the thread could break at any time, sending us into oblivion. Space may be big, but it's not empty. Our solar system brims with billions of comets and asteroids. The dynamics of our richly populated system make it inherently unstable, chaotic even. What this means is that, like the butterfly effect, we simply cannot predict where these objects will be if we go far enough into the future. On top of that, our knowledge of even nearby killer asteroids is incomplete. There could be something heading our way right now that we don't even know about. But humans have agency, we have technology, and we have an unshakable will to survive. So today, we're going to explore what we know about these threats, which ones really matter, and how we might save the world. When most people imagine asteroids in the solar system, they probably think of the asteroid belt that lies between the orbits of Mars and Jupiter, also known as the main belt. To date, we've catalogued over 1 million asteroids here, but unlike depictions in science fiction, the distances between them are still vast, typically 1 million kilometers. There's some quasi-famous members in here, huge asteroids like Vesta, Pallas, Ceres, and Juno, objects so large that we could one day live on them like the Belters do in the Expanse novels. In fact, these 4 are so big that when they were first discovered in the early 19th century, they were once considered planets. In fact, they would have been the 8th, 9th, 10th, and 11th planets ever found in the solar system because, of course, this is prior to the discovery of Neptune. Together, these large asteroids make up almost half of the main belt's mass, but even if you somehow scooped it all up into one object, that world would still only be just a few percent the mass of our moon. It's thought that Jupiter's gravitational influence prevented the belt from ever coalescing, and thus the main belt is, in essence, a failed planet. Like so many things in science, the more one studies the main belt, the more nuance and complexity one uncovers, because the main belt is certainly far from some kind of single monolithic population. Looking at it, one immediately notices 3 distinct belts: the inner, middle, and outer belt, separated by gaps named after their discoverer, Daniel Kirkwood, in 1866. So take, for example, the gap between the inner and middle belt. That occurs at 2.5 astronomical units, or AU. It turns out that this is the exact orbital distance from the Sun at which bodies would have an orbital period equal to precisely 1/3 of that of Jupiter, a 3-to-1 resonance, and hence that is why it is empty. And similarly, the gap between the outer and middle belt is caused by the 5-to-2 resonance with Jupiter. If one ventures further out, one eventually bumps into the behemoth, Jupiter. But even here, one still finds asteroids sharing the same orbit of Jupiter, but offset by about 60 degrees both ahead and behind, forming the so-called Trojans. Locked in place by Jupiter, these Trojans pose little threat to the Earth, but the belt is a different story. Here, the spiderweb of weak gravitational interactions between asteroids can perturb them into the hazardous Kirkwood gaps, where they are summarily kicked into more radical orbits by Jupiter, like a particle accelerator. Some of these can end up in new orbits which can be close to or even cross that of the Earth's, and this is the danger zone. We call these near-Earth objects, or NEOs.
At last.
It's estimated that over 90% of NEOs originally came from the main belt. In fact, every few thousand years, a kilometer-sized rock is injected into a near-Earth orbit via this mechanism. Of course, that also means that the main belt is slowly depleting, evaporating away about half of its objects every couple of billion years or so. So NEOs are largely former main belt asteroids, and they pose one of 2 main threats to the Earth, the other source of peril being the Oort Cloud, but we will come back to that later. A NEO is defined as an object which has a perihelion of less than 1.3 AU And remember, perihelion means the point in its orbit where it's closest to the Sun. Now, 99% of NEOs are in fact asteroids. Comets are pretty rare here. Those are defined as objects exhibiting coma or tails, and thus would likely be more ice-rich rather than rock. Given just how close these NEOs are to us, then of course that makes them easier for us to discover. Plus, we have a pretty good incentive to do so given their looming threat. In 1989, we were all caught off guard when a 300-meter-sized asteroid was detected to have just passed within 500,000 miles of the Earth. The United States Congress seemed to have noticed because in 1992, they mandated NASA to find at least 90% of the kilometer-sized NEOs within a decade. Now, NASA didn't actually formally adopt what became as the Space Guard mandate until 1998. That was 4 years after witnessing Jupiter get pummeled by the Shoemaker-Levy comet. It took NASA 12 years, but they did it, and we now know of 981 such objects. But we still don't have them all. Our catalog is estimated to only include 92% of them. So that means there could be roughly about 100 extinction-level event asteroids roaming around, regularly crossing the Earth's orbit that we have no idea about. Something to help you sleep at night, right? So why in 15 years since that mandate completed could we not grab the missing ones? There's probably about a dozen hiding behind the Sun in the same orbit as the Earth, but just opposite us. Unless we change our vantage point with a specialized spacecraft, those will be hard to find. But the lion's share of the missing NEOs are actually not those, but rather we are talking about objects on highly inclined and highly elliptical orbits. You see, existing surveys are optimized to find things along the ecliptic plane. That's the orbital plane in which the Earth resides. And these highly inclined NEOs are no joke. If they hit the Earth, they would do so with an impact energy up to 70% greater than that of the rest of the population. Now, fortunately, they are a little bit less likely to hit us. The impact rate is about 30% less, but still, that's pretty modest, and so these are a very major concern. Protecting ourselves from asteroids is definitely worthwhile, even if it's a small risk, but protecting yourself online is also crucial. So that's where today's sponsor comes in, Incogni. You know, it drives me crazy that these days you can't sign up for a new service without having to give away so much of your personal information that these companies then just often go on and sell to data brokers without your consent. They see your personal information as just another product, and they're willing to sell it on to the highest bidder. Things like your telephone number, employment history, address, and even your social security number. If you want to protect your personal information, you can fight back with Incogni. What's cool is that Incogni now has custom removals in the Unlimited plan and Family Unlimited plan. So if you find your personal information visible on a People search site or another website, flag it, and an Incogni privacy agent will take care of the rest for you. Sign up and they work to make you invisible again, chasing down where your personal data is and then using the full weight of the law to demand that your information be deleted. So check this out. For me, Incogni have now successfully deleted my personal information from roughly 1,000 sources, 1,000. And it would have taken me about 700 hours to have done that myself. So I am certainly glad to have the professionals' help. So sign up today at incogni.com/coolworlds and use the code COOLWORLDS for an exclusive deal of 60% off. Once again, that's incogni.com/coolworlds, code COOLWORLDS. Now back to the video. So far, we've been focused on the kilometer-sized NEOs, and for good reason. These would be devastating at a global level, but they are also quite rare, striking the Earth roughly every 1 million years. But the truth is that even a 140-meter-sized asteroid is a major threat, sufficient to obliterate cities, and those occur much more frequently, every 30,000 years or so. And just one of those would have an impact energy equivalent to 15,000 Hiroshima atomic bombs. So in 2005, Congress extended the Space Guard mandate down to 140 meters to be completed by the year 2020. Now, despite a lot of progress towards this goal, thanks to missions like NEOWISE, NASA hasn't been able to pull this off yet. We currently only know of about 38% of this population. But 2 upcoming missions should deliver the goods. Vera Rubin, which is just coming online, should find over 95% of the kilometer-sized NEOs and 60% of the 140-meter-sized ones over the next decade. And when combined with other surveys, that number rises to about 80%.
The Enterprise will be there. Maybe a little late, but we'll be there, sir.
But NEOs are not our only worry. Long-period comets hypothesized to be sourced from some distant population on the outskirts of the solar system, a population that we call the Oort Cloud, also strike the Earth with about the same frequency as NEOs. But in many ways, these are much more dangerous. For one, they come in highly elliptical orbits, meaning that their impact energy can be many times higher. Second, we have no way of detecting a comet that's nestled within the Oort Cloud. It's simply too far away. The only time we'll see them is when they're already on the way in. And what this means is that if such an object is on a collision course with the Earth, then we might only have a few months to brace ourselves. First proposed by Jan Oort in 1950, the Oort Cloud is pretty mysterious. We're not even really sure it's there. But there does seem to be some reservoir from which long-period comets keep emerging, and in the story of planet formation, it makes sense that there would be some icy population beyond the orbit of Neptune. It would be a huge spherical cloud with billions, perhaps trillions of icy planetesimals. Smushed together, the mass could be as much as 10 times that of the Earth, but it's incredibly diffuse, extending out to roughly a light year in radius. It's thought that interactions with passing nearby stars and even galactic tides periodically disturb the Oort Cloud, causing some of them to fling inwards. Really, the best we can hope to do here is to improve our lead time by detecting them a little bit earlier. In that vein, the Rubin Observatory is predicted to be able to detect about 40% of long-period comets 5 years prior to their perihelion, buying us precious time. But for the other 60%, we may have far less notice. For both NEOs and especially long-period comets, you might wonder, what chance do we have? How can we protect the Earth? And if one did hit us, how bad would it really be? In the paleontological record, we observe that about 3/4 of all plant and animal species, including all non-avian dinosaurs, suddenly disappear 66 million years ago. An astonishing event known as the Cretaceous Paleogene Extinction Event. The most likely culprit was the asteroid which caused the Chicxulub crater, buried underneath the Yucatan Peninsula in Mexico and radiometrically dated to occur within 32,000 years as the same time as this mass extinction. Radar topography reveals a 180-kilometer-sized crater, implying an impact energy of about 1 billion Hiroshima atomic bombs. The asteroid would have had a size comparable to Eros. We are talking over 10 kilometers across. To put this impact into context, as well as the other asteroids out there, we're going to use a logarithmic scale to sort of qualify how dangerous each of these are. So at the top of the scale, we have a 100-kilometer-sized asteroid. That's akin to a small moon. Such an object would completely obliterate the Earth's surface, likely liquefying the crust and boiling off the oceans. This is planet-wide sterilization, the end of our story. But beyond the moon-forming impact, which occurred during the solar system's formation, there's really no evidence for such impacts on the Earth. Next, consider a 10-kilometer-sized strike that would be akin to the last mass extinction, and something that knocked off most life, but not all. Life on Earth would eventually recover, but human civilization, I'd say, is cooked. Events like this happen roughly every 50 million years or so. Next up, we have kilometer-sized impactors, events that happen every 500,000 years or so. And these don't extinguish most species, but they would put extreme pressure on human civilization, triggering a multi-year winter as ejecta and dust block out the sun. This would cause global famine, societal collapse, and possibly a reset for humanity. Finally, we have the 100-meter class impactors, enough to destroy a city, but the damage would be largely localized. On a global scale, we might expect a few months of cooling, but we should expect civilization to persist. So with this context, we can see that through the Space Guard mandate, the US is trying to catalog all of the city to civilization-threatening NEOs out there. It's worth noting what a service this is for the rest of the world. The US taxpayer is essentially bankrolling the protection of the rest of the world here. Although, maybe they won't necessarily tell enemy nations of impending threats that could destroy their cities. Regardless, cataloging is obviously just the first step. Next, we have to continuously monitor and precisely calculate the path of these objects to assess just how dangerous they really are. A recent example of this was with the asteroid 2024-YR4, a 60-meter-sized rock discovered in 2024 with a slim chance of striking the Earth in 2032. Observations in January of 2025 reassessed the orbital path, and they nudged the impact probability up to 1%. The media started to get very animated at this point, and continued observations eventually bumped that probability up to a peak of 3.1%. That was on the 18th of February, sending social media into a frenzy. On the 11th of May, we pulled out our big guns, pointing the James Webb Space Telescope at it, which effectively ruled out an Earth impact. In fact, now it's got a 4% chance of hitting the moon in 2032, which would actually be fascinating to observe. But what if the story was different? What if we pointed judiciously at that asteroid and we found that it was in fact very likely to hit the Earth? With less than 8 years to go before the impact, NASA really wouldn't have a lot of time to design and construct a vehicle which could do much about it. Now, 2024-YR4 is about half the size of Dimorphos. That's a near-Earth asteroid that we actually tested out our first ever deflection mission on in 2021. The so-called DART mission was a kinetic impactor that smashed into Dimorphos at 14,000 miles per hour, thereby altering its velocity by about 50 millimeters per second. Whilst that sounds tiny, if performed a couple of years prior to impact, it would be sufficient to change the path by about half an Earth radius. Depending on how dead on the asteroid's path is to us, that already might be enough to save us. If not, we could always send 2 or more of those missions up to guarantee success. But at the end of the day, the important thing is that we have demonstrated such a mission like this, and so we have this option on the table. This is all well and good for a 60-meter-sized asteroid like 2024-YR4, but a kilometer-sized object is a completely different beast. DART would be little more than an annoying insect to such a monster. A key factor here is lead time. If we discover this object with centuries to go before the impact, then it would give us far more options in order to deal with it. For example, one elegant solution is simply to paint one side of the asteroid white, altering the albedo on one side and triggering a gentle nudge from solar radiation pressure. A similar option is to use lasers to trigger outgassing events on the surface, which would then act as little thrusters. Or we could actually land a machine that scoops up material and shoots it up into space, thereby creating an artificial thruster. Imagine for a second this large asteroid is represented by this cool world's water bottle. Then one option would be to physically park a large spacecraft right next to it whose mutual gravity would slowly nudge the asteroid off onto a new course. Now, this would of course require a very large vehicle and a huge amount of fuel to maintain position, so maybe this is a little bit beyond our current capabilities, but it is something we can investigate in the future. But if the impact is imminent on a timescale of say a decade or less, then there simply won't be enough time for any of these kind of long-term solutions. In that case, we will essentially have just one option, the nuclear option. The use of nuclear weapons in space is strictly prohibited under the Outer Space Treaty, so the first course of action would be to try to get emergency authorization from the UN to allow for such an attempt. Assuming we had, let's say, a few years lead time, then a single megaton nuclear warhead would be sufficient to deflect a kilometer-sized rock. But of course, the outcome depends heavily on the composition, density, and orbit of the body in question. The best strategy is probably not to detonate on or inside the impactor, as depicted in the movie Armageddon, since this risks fragmentation. Far better is to detonate about 100 meters or so away from the surface, thereby vaporizing the outer regolith. That plume of ejected material then causes thrust, thereby nudging the asteroid out of danger without fragmentation. But all of this carries risk of miscalculation or perhaps even a heightening of nuclear tension on the Earth if one nation acts independently of the others. So what we learn from this is that we have started on the right track. We have already detected over 90% of the kilometer-plus size NEOs out there, and we are building new observatories which should bring us up to near completion, as well as delivering most of the smaller threats too. But that cataloging process will take at least a decade to complete, and it is imperative we finish the job in order to give ourselves ample time to deflect them should we find a threat. But look, let's not be sensationalist here. The probability of even 100-meter sized comet or asteroid smashing into the Earth in a human lifetime is less than 1%. And even if it did, it wouldn't threaten civilization on the planet. The kilometer-sized rocks are far more devastating. Those can be game over events for us. The fact that there are still dozens of those marauding around the Earth undetected is a serious concern. Ultimately, the probability of a civilization-ending asteroidal impact in our lifetimes is very unlikely, but it is an event that we should reasonably want to take out an insurance policy against, since the risk is total collapse. But to be honest, in this current moment, I worry deeply about our capability to plan for risks which extend beyond a human lifetime. Perhaps it is a symptom of a selfish generation, one that only cares for its own direct experience and not for those of its descendants. Where are our cathedral builders? Who plants trees they'll never enjoy the shade of? Have we become too obsessed with the now? Climate change is the clearest illumination of this. The IPCC's AR6 Working Group 2 report finds it very likely will exceed 1.5 degrees Celsius of warming before 2040 under current policies, driving widespread freshwater stress, displacement of hundreds of millions of people, and accumulating hundreds of trillions of dollars in costs by the end of the century. At the same time, the 2024 Global Carbon Budget reports that CO2 emissions hit a record 37.4 billion tons. That's up 0.8% over the previous year, pushing us ever closer to irreversible tipping points like permafrost thawing. And look, even if you personally give this a small probability of actually transpiring, despite the chorus of climate science saying otherwise, it would be highly prudent to take out an insurance policy against said risk. The likelihood that the world will need an asteroid deflection mission in the next few centuries is just a few percent, and yet here, at least in the US, we have no problem collectively investing in that, as indeed we should. So if we think the probability of a climate catastrophe is even a few percent, then we absolutely should act. We can be the frogs slowly boiling away in the pot, not noticing our own demise, or we can activate our species' greatest superpower, foresight, to plan for things which have not yet come to pass. So, until next time, stay thoughtful and stay curious.
He has the power to wipe out the entire human race, and if we believe there's even a 1% chance that he is our enemy, we have to take it as an absolute certainty.